welcome all from different time zones, from different countries. So we would like to invite Leo Mozar for this webinar as the guest speaker. So Leo is an open source silicon advocate and aspiring chip designer, and he obtained his master's degree from Grace University of Technology, majoring in microelectronics and IC designing. So he designed the Greyhound, which is a RISC-V system on chip, with a tightly coupled fabulous eFPGA fabricated on IHP's SG13G2 process, which we are using in this marathon. So previously, Leo also worked with eFabless, and where he focused on enablement for the IHP open source PDK on analog automation with CACE. So he's excited about various open source Silicon community, and yeah. So welcome, Leo, and we hope to hear from you a lot of insights on IHP PDK and lot many other things and Greyhound and yeah. So welcome.
Hello, everyone. Thanks, Sumanto, for inviting me here. I'm really happy to be here, and hopefully I can show you a number of things that are interesting. So, as Sumanto has already said, I'm going to talk about FOSSi, free and open source silicon in general, then about my chip Greyhound that I did as part of my master thesis, and also about LibreLane, which is now the successor to OpenLane, if you have heard of that, and which I have also used to implement Greyhound. Yeah, but first, again, just quickly about me. Yeah, I'm an open source silicon advocate. I've submitted to several of the open MPW shuttles. So back in 2020, when Google did these open MPW shuttles, I also submitted some designs back then. Yeah, for my master thesis, I did this Greyhound chip that I'm going to show you. During my master's, I also worked at eFabless, where I worked on for one case, which is the circuit automatic characterization engine. I also did some bring up for Magic on NetGen for the IHB Open PDK, and I also improved the OpenLane 2 support for IHB. And OpenLane 2 is now LibreLane, if you're wondering. And currently, I'm doing work for Wafer.space. So Wafer.space is also an MPW provider for the GF180 MCU process. And there I'm developing a full chip LibreLane template. I also do some work on the PDK, and I'm working on the reticle stitcher. So to get all of the projects into a single project into the reticle. And yeah, you can talk to me on FOSSi I'm Leo on fossichat.org. So if you have any questions or also there are various rooms for different topics. You can ask a lot of questions there. So just a quick overview of some of the chips that I did. So one chip that I did during the open MPW shuttles is the one on the very left. So this is the where I did a simple RISC-V core and the SoC with some true random number generators. This one was on GF180 MCU. Then I did another one. This was actually this year, Panamax FPGA, which was on Sky 130. And this one includes an embedded FPGA. You can see this as this kind of regular structure there, and also some SRAMs on the side, dual ported, and some analog macros. And then I did also Greyhound, the first revision, which was my master thesis. And then I also did a second revision with some improvements. And I'm going to talk about Greyhound in detail later. But first, the open source silicon story so far. So as you may already know, back in 2020, the Sky 130 PDK, the process design kit, was released, which was very special at the time, the first open source manufacturable PDK. And after that, in 2022, was also the GF180 MCU PDK released for a different process. With a bit of a larger feature size, but still very interesting. And yeah, since you're also using the IHP PDK, this one is in development since 2023. It targets the IHP ST13G2 by CMOS process, or also there's also now the CMOS only variant. And this PDK is also still in active development, so there's a lot of work happening there. Yeah, and also one great thing about these things being open source is if you have open PDKs, you can also do open design. So not only the RTL is open source, for example, but really your complete design can be open source down to the layout. And with that, you can again improve the tools. And once you improve the tools, you can also again improve the open PDK. So this is this open source EDA development cycle, continuously improving things. And I think for students, this is also very important, these open PDKs, because you can just freely access the PDKs, create designs yourself. That's how I got into this whole space. So back in 2020, when the first PDK was open sourced, I took a look, and since then I'm part of this space. And especially for universities, this can be quite convenient, because no student has to sign an NDA, as you are aware. So chip design becomes really attractive again, also at universities. There were a number of free open source tapered programs. Unfortunately, they are discontinued by now. So there was this Open MPW tapered program, which was sponsored by Google, and eFabless at the time managed the shuttles. And there were runs from MPW1 to MPW8 on Sky 130. And there was GFMPW0 and GFMPW1 for global foundries for the GF180 MCU process. Early on, there were some issues on the chip in the design, some hold violations in the GPIO configuration. But despite that, they still got the chips working, and these issues were also fixed in later revisions. And there was also this free MPW run funded by the BMFDR in Germany, which was for the IHB PDK and for their SG13G2 and SG13 CMOS process. There were 7 shuttle runs from 2024 to 2025. And I also submitted Greyhound to one of those shuttle runs, and I'm expecting the chips for Greyhound soon. However, there you don't actually own the chips because it's publicly funded. It means you only you loan the chips, so you can use them to do measurements. But after I think 2 years, you have to give them back. But I think that is quite fine. So unfortunately, these open shuttles are not available anymore, but there are a number of paid tapered services. So the first one is Chip Foundry for the Sky 130 process. I took some numbers from the website about the cost and what you get, and also the turnaround time. There's also now Wafer.Space for the GF180 MCU process. Kind of a different offer. Also maybe faster turnaround time. But the first shuttle for Wafer.Space is only going in December. And for IHB, they do now also offer a low-cost open source MPW access, where, depending on the process, the cost is different. But for which we have open source PDKs, they are to get chips fabricated. I think the most important one is Tiny. Previous services, they do the designs on a reticle, and Tiny just subdivides this into even more smaller, make it even cheaper to manufacture your own design. And they offer shuttle runs on Sky 130, SG13 CMOS, and soon they will also again on all three of the processes with open source PDKs. And they also do really cool competitions. For example, there was the demo scene competition. So these are all great options. Probably you have heard about some of them already, but just for completion. Now you know every option. And with that, I would like to continue now with Greyhound. So Greyhound is a RISC-V system on chip with tightly coupled embedded FPGA on IHB SG13G2. On the right, you can see the layout of Greyhound. At the bottom is the SoC, the system on chip, and the top part is all the embedded FPGA. On the right, we can also see the SRAMs that I've connected here. And yeah, so you can view the source code here, and Greyhound is currently being manufactured. And yeah, now you should see the top level block diagram, if that is working. So as already said, on the left, there is the SoC with the CPU connected to all of the peripherals. There was no space for a crossbar, so the area for the SoC was limited. On the right, we have the embedded FPGA fabric with the SRAMs, and it is configured by these frame data and frame drop signals and the fabric configuration module. So basically, you just input the bit stream and that it will configure. But there are several ways to get the bit stream into the embedded FPGA. So you can do this with this SPI peripheral or SPI controller. So on startup, so there is a pin on the chip which is called FPGA mode, and you can either pull this high or low. And if it's if it's pulled down, then it selects I think the SPI controller, which means on startup it will fetch the bit stream from an external SPI flash. If it is pulled the other way, then the SPI peripheral is active, and basically it will just wait for data via the SPI bus, so you can use your favorite microcontroller to supply a bit stream. But there is also the possibility to configure the eFPGA from the SoC. So there's a special fabric configuration peripheral over which you can send a bit stream, or you can also just trigger a reconfiguration. So the CPU doesn't have to do anything. You can just wait until the fabric has reconfigured. And once the fabric is reconfigured, so this is also connected to the fabric, which is not shown here, but it can then act as a custom peripheral, which connects to the SoC, or it can act as a custom instruction. In the first revision of Greyhound, it can only be one of those things at once, but we'll take a look at the later revision later on. So let's continue with the system on chip, slide 15, you should see now. So taking a closer look at this, as already said, I'm using the CV32E40X RISC-V core. And I've chosen this core because it already has a custom instruction interface. So it was quite easy to connect the embedded FPGA to this interface. I also enabled a number of standard extensions. So it's a RISC-V32 IMAC with some additional extensions, which provide some performance improvements also. There's some SRAM also on the chip. So at the bottom, you can see the SRAM for the SoC, 8 KB in total. There's the quad SPI execute in place flash controller, from which all of the data is fetched. And this controller also includes a small cache, so 8 lines of 32 bytes, direct mapped. And this cache is quite useful because the main bottleneck of the system is getting the data into the chip. There's also a quad SPI PSRAM controller to extend the available memory, the available RAM. There's a UART for communication and debugging purposes, and then you can access the eFPGA, the peripheral you have implemented in the eFPGA also. Now for the eFPGA fabric, this one was generated using Fabulous, and on the right you can see the tile map. So I'm now on slide 16. So the most important tile is the CLB, which stands for Configurable Logic Block. And this one contains 8 4-input lookup table and also 8 flip-flops, as well as one large multiplexer, but this one is not yet used in the automated flow. But with these lookup tables and flip-flops, you can implement any logic function and any design you want. Then on the left, we have these I/O tiles with 2 I/Os each. So for 32 I/Os in total. There are also some, so we have these SRAM tiles to the right, which connect to the SRAM macros. We have some multiply accumulate tiles, which can be used, to implement multiplications and additions dedicated. So this is faster this way and uses less resources. And there's also one column of register file tiles, which can be used to implement register files, for example, for an RISC-V CPU. The whole eFPGA has one global clock network, which is not a feature, but that's just the current limitation of Fabulous. But that might change in the future. I also implemented some custom tiles. So these tiles above, these are the default tiles that come with Fabulous, but I also implemented some custom tiles. A warm boot tile, which allows you to select one of 16 slots, and then you can trigger a reconfiguration, and the embedded FPGA fabric will reconfigure itself from an external SPI flash. There's also the CPU IRQ tile. So with this one, you can send interrupt service requests to the CPU. And then there are these CPU interface tiles down here, with which you, so these implement the interface to the CPU and to the SoC for the custom instruction extension and also for the custom peripheral. Now I'm on slide 17, just a closer look at the configurable logic block. So as you see, we have 8 times 4 input lookup table with flip-flop at the end. So this is one LC, one logic cell. There's also some carry logic in front of the lookup table for faster additions, and some shared logic for the clock, enable, and set reset signal. As you can see, there's also this large multiplexer at the end. It is currently not yet used in the automated flow, but it could also allow for a more efficient mapping of the design. Now, how do you actually implement a design for the FPGA? Well, for this, I also use the Yosis and NextPNR open source toolchain. So Fabulous automatically creates a model of your FPGA for NextPNR. So this works automatically. So Fabulous creates these files once, and then you can just use them. So for Greyhound, they are already created. And if you want to implement a design, you just go through the flow on the right. So you provide your Verilog sources. They will get synthesized using Yosis into the design.json. And then this gets passed on to NextPNR together with the bells and pips file. So bell stands for basic element and pips for programmable interconnect points. So they describe the embedded FPGA. NextPNR can then do the place and routing of the design, creates the design.fpga assembly file, and this can then be assembled with the bitstream spec into the final bitstream. So I tested some designs on the embedded FPGA. So of course you can implement custom instruction extensions, custom peripherals, but I also wanted to try if a RISC-V core actually fits onto the eFPGA, because it's not really large. There are around 700-800 lookup tables available. But as you can see, both the GWRF, so it's a 4-bit RISC-V CPU, so still a full RISC-V CPU, but 4 bits are processed each cycle, and also the FASI RISC-V in a bit serial variant. And yeah, both of them fit into the eFPGA, only barely, but they fit. And comparing this to an ICE40 UP5K, the resource usage is quite similar.
So Leo,
Okay.
I have one query.
Yeah.
So this Yosis and NextPNR were run independently or as a part of the LibreLane flow?
This is already afterwards. So after the chip is implemented,
I see.
the whole chip is implemented using LibreLane. So for the embedded FPGA, I generate the RTL netlist using Fabulous, and then I implement all of the tiles with LibreLane and stitch the fabric together. I will actually show this in the next slides. And also then for the full chip, this is also implemented with LibreLane. So LibreLane implements the chip, and
Mhm.
after you get the chip, you want to implement a design for the embedded FPGA. So you want to create a bit stream that is then in the embedded FPGA, and that
Oh,
is
I
done
see.
with this flow.
Mhm.
Mhm.
Got it.
So
Yeah.
with Yosys and NextBin are here. But actually Yosys is also used in LibreLane. So Yosys is used for LibreLane and also for the FPGA design flow.
Yeah, therefore I got a bit confused because yeah, it's also there in the LibreLane, so it's
Yeah,
used here as well. Oh, I see.
it's quite versatile for
Yeah,
ASIC
yeah.
and for FPGA synthesis.
Mhm. Correct.
Yeah, and yeah, actually now we come to the physical implementation. So that's where I explain how the tiles are implemented using LibreLane. So we get this tile map that you have seen before, and for each tile, we implement it using LibreLane. And for this, I created a plugin, so a fabulous plugin for LibreLane, which provides two flows, the fabulous tile flow and the fabulous fabric flow. And the fabulous tile flow is used to implement each of the tiles or each type of the tiles. So it places all of the standard cells, places the pins and also the power straps in such a way that you can then connect the tiles together. This is done with the fabulous fabric flow. You can configure everything with some configuration variables. But basically, after you have implemented all of the tiles, you can just stitch them together. So you just place the tiles next to each other, and the pins, they all align correctly up already. So this is quite a fast step, actually. And with this, you can then stitch the complete fabric. Yeah, and then for the full chip, so I've got the eFPGA as a macro here. So the eFPGA is stitched together, but now I need to finish the full chip. Um, this is also done with LibreLane. And at the time, this proved to be difficult because there were hold violations in the chip. And hold violations are really bad because you can't just clock your chip slower, as you could do with setup violations, but hold violations, they are really a problem. So I debugged this a bit, and it seems that the RC estimates um, compared to the SPEF extraction were just quite different. And therefore, the clock tree was skewed, which led to hold violations. And my workaround was to limit the core area. So initially I allowed cells to be placed to the left of the embedded FPGA, but my solution was to put a blockage there to disallow this, because then all of the standard cells are at the bottom and the clock tree is much better balanced. It was not a best solution, but given that the tapeout was in 1 week, I had to finish this, and this solution worked for me. And it seems so. Back at the time, there was also a bug in OpenRoad. So LibreLane uses OpenRoad to do the physical implementation. And there was a bug that the vertical layer resistance in clocknets was not considered. And yeah, this bug was fixed. And I thought, okay, maybe this bug led to this issue, but actually it was something else. But I will talk to this later. The next step, of course, is verification to make sure that the chip will actually work. So I created my test benches with CocoaDB. CocoaDB is a Python-based test bench environment. So I'm now on slide 25 that you can see. So basically, you implement your test benches with Python, which is quite nice because you have all of the Python packages available. And yeah, for that, I created a test bench just for the system on chip. And I did an RTL and gate level simulation, and all was green, as you can see. I also simulated just the fabric on its own. There I could only do an RTL simulation because the gate level simulation had issues with the fabric, because the fabric, because of its nature, There are a lot of logic loops inside of there. And with Icarus Verilog, the simulator that I used, this resulted in a lot of X unknown states everywhere. So I couldn't do gate level simulation, but from the previous Open MPW shuttles, there were also some fabulous eFPGAs taped out and they worked fine. So I can be quite sure that the fabric on its own will work. And on the chip top level, I then also did an RTL and gate level simulation. I also did an abstract LVS. Why just abstract? Because the extraction of the IO cells did not work that well at the time. The PDK is still in development, but I think this has been fixed in the meantime. But for Greyhound, I only did an abstract layout versus schematic check. And I also did the minimal design rule check, DRC, because this was needed for the submission. And it covers the digital design rules quite well. So I only use the predefined standard cells, SRAMs, IO cells. They are already LVS and DRC clean. So the minimal DRC check should be fine.
So the simulations were
Um,
done in which tool?
so the test benches were written with CocoaDB,
Mm-hmm.
so in Python.
Okay,
But in CocoaDB, you can then select any simulator. So you can select commercial simulators or open source simulators. You can select Verilator or Icarus Verilog.
I
And
see.
for this, I chose Icarus Verilog.
Mhm.
Yeah, because Icarus Verilog also allows more states. So not only 0 and 1, like Verilator, and it can also read in like the standard cells for the gate level simulation. So that worked quite well for me.
You're correct. Thanks.
Mhm. Yeah, you're welcome. And then on the right, you can see the static timing analysis results. So in the fast corner, the chip runs. So this is now only for the system on chip. Uh, the embedded FPGA, the speed of your design in the embedded FPGA, it depends on your design, of course. And right now, Fabulous does not have a way to get a timing estimate for the design, but this will be fixed in the future. So these SDA results are for the system on chip. In the fast corner, 85 megahertz, in the typical corner, 55 megahertz, and in the slow corner, 34 megahertz. So I'm keeping my fingers crossed that the chip will work. At the end of October, it should come out of the foundry, so we will know then. Um, yeah, for Greyhound or for the first revision of Greyhound, I would like to thank my supervisors back at my university, Tobias Scheipel and Meinhard Kissig. Also the fabulous team which are split across the Heidelberg University and University of Manchester, for their help when I had questions, but also for being open to improvements from my side. Also thanks to the open source team at IHP for actually developing the PDK and for continuously improving it. Also thanks to Tim Edwards at Open Circuit Design for his help back when I was at eFabless and also even now. And also to the BMFDR for funding these open shuttle runs, because without them, I couldn't have taped out Greyhound. Um, yeah, but I already did a second revision of Greyhound. So there were a number of things that I wanted to improve. And well, I did improve them. So first of all, I updated LibreLane, which updated OpenRoad to the latest version. So there's now a better antenna diode insertion strategy in use, so less antenna violations. There's also an update to the HB PDK, which got new standard cells in the meantime, improved standard cells, and also SRAM. So more SRAM configurations, also with dual port. I also did a hierarchical implementation of the SoC. So the first revision was completely flat, and now I keep the hierarchy on the larger modules in the design. This way I could increase the density, so the placement was better, and I could also double the number of cache lines. Previously, in Greyhound Revision 1, I used SV2V, a tool to convert system Verilog to Verilog. But now I use Yosys Lang to read in system Verilog directly. And Yosys Lang is already supported by the LibreLane development branch. Then for the eFPGA, I
So
focused,
this system Verilog to Verilog you said, right?
yeah, SV2V. It's a tool which converts system Verilog to Verilog.
Why is it needed, by the way?
So for the Greyhound, yeah, for both Greyhounds, I use this CV32E40X RISC-V core,
I
and
see.
it uses quite a lot of system Verilog features.
Mhm.
And Yosys by default only supports a number of system Verilog features,
I see.
so it couldn't read it in, and that's
Mhm.
why I had to convert it. Yeah,
I
but
see.
now with Yosys Lang, I can read it in directly because this connects to Yosys as a plugin, and yeah, it just works.
I see. And another
Mm,
thing is, what do you recommend us to, like, if some of us want to contribute to the IHP PDK and add new standard cells? So what is the
mhm.
procedure and so on? Like,
New standard says. So I think there was this competition. I forgot what it's called. But they also did some new standard sets for the GF PDK. Um, there was a room on FOSSi chat for this.
Mhm.
And I think, yeah, probably it's just best to take a look. So the question is, do you want to develop a completely new standard cell library, or do you just want to extend the existing one?
Mhm.
Because then you can already use the same cell height uh, and everything. So you just make sure that it also fits in this same standard cell row height as the other cells. And yeah, you draw the schematic of your cell. You do the layout either with Magic or K layout, and then you need to generate the different views, like the left view, the GDS. Of course, you draw yourself, and there are
Mhm.
also some tools to characterize the standard cells to get the Liberty view. I think there's one called LC time. There's one called charlib, and also some others.
Mhm.
And once you have all of these views, you can add them to the library, and LibreLane can then, yeah, basically just use them to do the place and route using open route of the cells. So that would be the procedure. But I haven't actually done this myself, so probably best to ask on FOSSi chat what is the best procedure for that.
I see. Yeah, thank you.
Yeah,
I
you're
think it's
welcome.
called the Chipathon. I think Tim
Yeah,
Edward is a part of that.
exactly. Yeah, it was the Chipathon for Global Foundries 180 MCU. Thank you. Yeah.
This the standard cells were converted from GF180 to IHP or like something else.
Um, uh, so in the Chipathon, they didn't do anything with IHP, as far as I know. This was just a GF, and they created some standard cells from scratch
Mhm.
to extend the standard cell libraries. But actually, the standard cells that are available in IHP, they were ported from the Sky 130 standard cell library, from what I know. So they actually from Sky 130 moved to IHP and then also optimized a bit. So that is also quite interesting to know.
I see. Great. All right. Yeah.
Yeah. Okay. So let me then continue here. So yeah, I extended the embedded FPGA. I could increase the lookup tables to 1024, the DSPs to 8, and also the register files to 16. And in this revision, I could also create a dedicated custom instruction and peripheral interface. So you can have a custom instruction and peripheral in the eFPGA at the same time. And I do now have still some SRAMs, but also some block RAMs with half of the data width and yeah, two read-write ports. So you can actually use them as block RAMs in the FPGA. So that are some quite nice improvements. Yeah, this is the layout for Greyhound Revision 2. And again, this is the link to the repository if you want to check the source files out. All right. Are there any questions to Greyhound or to anything related? Because afterwards I will continue with the LibreLane presentation. All right.
Yeah, okay, sounds good. So, yeah, so thank you for your wonderful presentation, and it was very much insightful to know about various things about the
Yes,
LibreLane,
I will continue with the LibreLane presentation.
yeah, LibreLane and your the Greyhound SoC which you have developed.
Don't worry.
So I would want the audience to ask you some questions, to post questions here, because it's a wonderful
Mhm.
opportunity to interact with Leo. So one of them have asked, does this open source flow support transaction level Verilog, TL Verilog?
Uh, so I don't really have experience with transaction level Verilog, but maybe there's also a way to compile it down to something that Yosys can read. So basically, Yosys is the synthesis tool for LibreLane.
Mhm.
Everything that you can read with Yosys, you can get into the flow. There are a number of plugins for Yosys. So, for example, the Yosys Slang plugin to read system Verilog. But there's also a plugin for VHDL. If you want to read in VHDL instead of Verilog, that is also possible. And maybe you can compile this down to something that is compatible.
Yes, so let me answer then. Yeah, thank you for your answer. So basically, this transaction level Verilog can be converted to system Verilog using Sandpiper SAS,
Mhm.
yeah, so that system Verilog, as Leo mentioned, can be used system Verilog to Verilog, and Verilog can be used for Yosys
Mhm.
synthesis.
Or you can read it in using the Yosys Slang plugin
Yosys
directly.
lang, yeah.
So yes. Mhm.
Yes, so this is done. And Girish is asking, how did you fix hold time violations?
Yeah, exactly. So in the second revision, as you can see now, um, I could place the standard cells on the very left, and I thought that the bug fix in OpenRoad would make this possible, but actually the issue was still there, and it turns out that OpenRoad they did a calibration on the RC constants. So the RC constants that come from the tech lab, they are actually not perfect. They can be calibrated to better match the SPEF extracted um, version of the timing information. So basically, they take a number of representative designs and run the flow over these and calibrate the RC constants until they better match the SPEF extraction. And they then push these constants. I think it is in the OpenRoad flow scripts repository. And I just used these constants and added them to the LibreLane configuration for the IHP PDK. And with these constants, the clock tree was much better balanced, even when I placed the standard cells next to the embedded FPGA. So yeah, that's just an improvement there to use the calibrated RC constants. And I will also push that change to the LibreLane configuration for IHP so that everyone will have these improvements. All right.
So I think you're
Which
muted.
communication protocol is used between RISC-V SoC and FPGA?
RISC-V SoC and what?
FPGA,
And FPGA. Mhm.
yeah.
So the CV32E40X, it has this custom instruction extension interface, also developed from the Open Hardware Group.
Mhm.
Um, I don't know the name exactly, but yeah, it's a standard interface, and you can then connect accelerators to it. And in this case, the embedded FPGA implements the accelerator. So that's how it is connected. And how is it connected to the SoC, to the peripheral? So for the SoC, I use the Open Bus interface, OBI. So the whole SoC uses this bus interface, and this bus interface is then also just connected to the embedded FPGA, and this way the embedded FPGA can implement a peripheral.
Okay, great. So, yeah. So, will you be talking about LibreLane as well right now?
Yes, there is another whole presentation planned for this, so it would be here.
Okay, yeah. Please feel free to do
Mhm.
so.
All right, then I will continue with LibreLane, and
Yeah,
after this presentation, we can then again talk about maybe some LibreLane related questions.
sure, sure.
All right. Yeah, so this presentation is from my side, Leo Moser, but also from Mohamed Gabbar, the developer of LibreLane. So Mohamed Gabbar, aka Don, if you see his name on GitHub. From my side, Leo Moser, and also Mohamed Gabbar, and he was the lead developer of OpenLane 2 back at eFabless, and OpenLane 2 was then moved to LibreLane after the shutdown of eFabless. So LibreLane is now the community maintained fork of OpenLane 2, where now all of the updates are happening. So I'm now on slide 32. The big announcement that was back in July was that LibreLane was now officially released. And yeah, with that now development can continue. And as already said, the big change is that LibreLane is now community maintained. So there's not a single company behind it, but there are multiple companies like Tiny Tapert, Chip Foundry, Waferspace, or also IHB that are using LibreLane. And therefore, they also want to improve LibreLane, but there's not a single company behind it, which in my eyes is a good thing. So, but as already said, the background. So LibreLane started as OpenLane back at eFabless. And this was in 2020 when the first Sky130 PDK was open sourced. And eFabless, they needed an free and open source end-to-end flow. And there was none available at the time. So that also included DRC and LVS checks and everything to get a design ready for submission. And that's why eFabless developed OpenLane. And it was a success. So there were hundreds of designs were created with OpenLane, which were put on these OpenMPW shuttles. However, there were also a number of limitations of OpenLane because it was developed on a very strict deadline. There were a lot of architecture shortcuts taken. For example, it was difficult to run just parts of the flow. There was no standard way of reporting data about the design, metrics. It was also other tools to the flow. It was written in Tcl, which is do a good framework in Tcl. So that's why OpenLane 2, or now LibreLane, was developed, and it was started as a ground-up rewrite of OpenLane. It was named OpenLane 2 back at eFabless. The goal was to be backwards compatible with OpenLane 1, and it should provide a fully customizable Python-based flow infrastructure. On the left, this QR code, or also the URL you can find in the LibreLane repository. It links to a Colab notebook where you can just check out LibreLane directly in the browser. So you can give this a try. Now I'm on slide 38. So the design goals of LibreLane were, of course, to retain the simplicity of OpenLane. So it should be quite straightforward to get from your RTL to the final layout. But LibreLane should also offer robust packaging. So OpenLane 1 provided a Docker container. LibreLane still provides a Docker container, but you can also use the Nix environment. So basically Nix is a package manager, and it allows you to provide all of the dependencies, all of the tools that are needed for LibreLane to run. And these tools, they run natively, so you have no loss in performance, but still all of the dependencies are made sure that they are available. So this is really great. And
So
also LibreLane,
LibreLane is
yeah,
available on Nix and Docker. Does it have a Docker support or something?
yes. So if you
Available?
go to the LibreLane repository, there's then also the read the docs documentation, and then a starting guide, and there you can then choose how to install LibreLane. And there is the Dockerized mode. So basically, you just install LibreLane using pip, a Python package manager, and then you can run LibreLane with the Dockerized option. and it will start a Docker container in the background and run all of the tools this way.
I see.
So that's one way to run LibreLane, or you use the Nix backend, and this way you also get the full performance out of LibreLane.
Correct. All right. Sounds good.
Mhm. Yeah. So here's an architectural overview of LibreLane. It consists of these 4 modules, as you can see. The state module, so a state in the sense of LibreLane, um, is basically a collection of design formats which maps to a file on your disk. So basically, you have a left design format, and it points to a left file on your computer, or for example, the layout or your RTL. So this is just the current state of your design. And states are immutable, so you cannot directly change them. You can only ever create a copy of a state and then change this copy. And this is important because this way you can always go back to a previous state in the flow and then maybe run the flow with a different variable, or just run parts of the flow. All of that is possible this way. Then a step, it performs a transformation on a state. So there are steps, for example, for OpenRoute to do the routing, or for KLayout to do the DRC check. So a step works on the current state. It maybe just does some checks, or maybe it changes the state, creates a new state, and then this is then used by the next step. And you could just call step after step, but that would be quite cumbersome. So for that, the flow module exists. So a flow just calls step after step, one after another, and there are sequential flows, but also flows for design exploration, which will just continuously run a flow until a certain metric is below a value. So that is also possible. And finally, there's the configuration module, which just takes all of the configuration variables and checks their type and passes this on then to the flows and step modules. And all of this is accessible via the LibreLane Python API. So you can directly use LibreLane from Python. You can write your Jupyter notebooks, or you can call LibreLane from the command line. And now an example, how would this look like for the classic flow? So first of all, we need a design. So on the right, we have a simple 8-bit counter in System Verilog. I'm now on slide 41. Then on the left, we have a short configuration file. So you can configure LibreLane with a configuration file. This can be in Tcl, JSON, or YAML. And here we specify the top level cell. We specify all of the Verilog or System Verilog files, the clock port of the design, and also the clock period. Because LibreLane will automatically create an STC file for you, but you could also just provide your own STC file if you prefer that. And then you simply call LibreLane with your configuration.yaml, and yeah, LibreLane will run through the whole flow. So here we are at step 46 of 79 in the detailed routing step. And once it has completed, you can then view the design with the open in OpenRoute flow, and then you can actually see the implemented design. So in this case, an 8-bit counter on Sky 130. But the cool thing about LibreLane is that you can easily switch the PDK. So you just provide -- PDK, Sky130A, GF180 MCUD, or IHB SG13G2, and LibreLane will implement the same design for different PDKs. So in all cases, this is an 8-bit counter, but it's implemented using different PDKs. All right, so community and support. Currently, the supported PDKs or open source PDKs are Sky140 and GF180 MCU, both in the main branch. And IHB SG13G2 is also already supported, but support for IHP is still in the development branch. So we're working on the next release. So IHP will also be soon in the main branch, but for now, this is in the development branch. And you can also support proprietary PDKs. You just have to set up a LibreLane configuration. And actually, the University Heidelberg, for example, is doing this for the XFAB, for one of the XFAB PDKs. But of course, this PDK is proprietary, so it's under an NDA. You have to sign an NDA to access it. But if you sign the NDA, you might also then access the LibreLane configuration from University Heidelberg. Just then need to talk to them. All right. So we have some success stories here. So LibreLane, or back at the time it was OpenLane 2, was successfully used at eFabless for internal development. So at eFabless there was the Frigate chip developed, and it used already OpenLane 2. Was a really nice chip actually, but unfortunately it didn't get manufactured because eFabless got shut down before that. But the RTL code for Frigate is actually, it was open source, so that is available. Tiny Tapeout, of course, uses LibreLane, so they already switched from OpenLane 2 to LibreLane. Chip Foundry, they're also using LibreLane, and wafer.space, I'm doing the LibreLane template for wafer.space, so here you can also already use LibreLane for the implementation of the chip. So the community. So please join fossichat.org. There is a LibreLane room where you can ask questions, or also help others if you want. So please take a look at this. And to get started with LibreLane, take a look at the documentation. There's also a migration guide if you started with OpenLane, but also just an installation guide of LibreLane when you just start out completely new. All right, and with that, this was LibreLane, and if there are any questions, I can answer them now. So
Yeah,
I'll
thank
try
you.
to
So, yeah,
start
there are
my
a couple
video
of
now,
questions again.
please.
So, yeah, did you include any DFT design for testability? This is with respect to, I guess, your design, Greyhound.
Mhm.
Did you include any DFT scan chains within your design for fault detection after packaging?
Not yet, but that is something that I would like to do. Previously, there was, I think, was it a LibreLane plugin already? But it is called Ford, and it was developed by the AUC, American University of Cairo, um, and which does the scan chain insertion for a design. But Ford is now more or less outdated, and Don, so for his master thesis, he's actually working on a new DFD plugin for LibreLane, which will be actually much better. Let me just search for the link, then I can send this into here. So it is called Defetto, and yeah, it's an open source DFD flow, still work in progress, but it should be already good to use, ready to use. And if there are any issues, just open issues in the repository. So I sent in a link into the chat to Defetto.
Okay, and there's another question. XFAB is on which node?
Um, I'm not exactly sure which node they're using for that, but XFAB, they provide several different nodes. So I think also maybe from 130 nanometers to also larger process sizes. You would have to take a look at that. Yeah.
Okay, and yeah, anything else? Any other questions, audience? Please feel free to ask here. It's a wonderful opportunity to interact with Leo.
Yeah, and definitely join FOSSi chat if you can. There are also already a large community there of experts also, and people that are just starting out with the open source tools. Yeah, so.
Okay, there's another question from Aditya. So Aditya is our team member. So
Mhm.
that's LibreLane. So he was asking you related to one of the takeout sessions. ISP. Anyways, so does LibreLane currently support patterning generation step for all PDKs?
Um, Yeah, that's a good point. So I'm currently working on this pattern generation step, and it is not yet upstreamed into LibreLane. So it's still a separate branch, but I will upstream it soon. And this already, it works for IHP. So I've used it for Greyhound for the pattern generation and also for GF180 MCU. So let me just send in the project template for GF180 MCU into the chat. So this one is for wafer.space and can be used to generate the complete chip um, before submitting it to the shuttle. And this also uses the same pattern generation step. So it works for IHB, it works for GF. Does it also work for Sky 130? It should in theory. I haven't tried it, but the problem with Sky 130 is that the I/O cells are quite complicated. So not sure how much sense it makes there. So back at eFabless, Tim Edwards created this template patterns. So it was called OpenFrame and then also Panamax. Because he also did a lot of additions. He added some constant cells for each I/O so that you can just connect them. And there you also have two different voltage domains. So it's not quite that easy. But in fact, you could use the so for on IHB, the I/O cells they were actually generated using I think it is called the chips for makers or Arakeen project from Staff Verhagen. So these I/O cells were generated, and you could generate the same I/O cells also for Sky 30. And if you do that, they are then quite easy to use, and you could then create the full patching using the patching generation step also on Sky 30.
I see.
Yeah, that is the current state. Thank you.
So yeah, so this what about the PDK SF7? So there is some support with this. It is a predictive PDK, I guess. So
Which PDK again?
ASAP 7.
Yeah. There are some, yeah, ASAP7 and I think 3 PDK45, for example. Yeah, these are PDKs that are non-manufacturable, but you can still use them for designs. And they are not yet officially supported by LibreLane, but you could create a LibreLane configuration file for those, and then you can also just use them in LibreLane. And unfortunately, we are currently working on other aspects of LibreLane, so we don't have enough time for that. But if anyone wants to do this and yeah, create these LibreLane configuration files, that would actually be really great.
Okay, sounds good. So thank you a lot. Thanks a lot for this wonderful, insightful webinar. And yeah, got to learn a lot of things. I hope the participants also have an enriching experience from your webinar.
Mhm.
And yeah,
Yeah, happy to be here. Thank you for inviting me here. And yeah, have fun working on open source chips.
yeah.
Thanks a lot.
Thank you. Thanks a lot.
Goodbye.